Hi there. This video is for section 3.9, where we're doing some word problems, in other words, applications of the chain rule using many variables, three or more variables. This video picks up where we left off in my previous video, which was a review on section 3.7, specifically with two variable related rates problems, these word problems with the chain rule. So we ended up with a little more complicated version of that using several variables as a warm-up for this video. And that was about this right triangle that's expanding over time. We have side lengths of x, y, and z. And we ended up with this particular formula that the rate of change of z was given by this. The way we came up with that is we wrote down the Pythagorean theorem, x squared plus y squared equals z squared. Since we're looking for dz dt, we differentiate with respect to t. We did our chain rule, and we solved for dz dt, giving us this wonderful formula right here. So we're going to pick up here on example A. We have the right triangle. It's just like we did before. So we're going to be able to use the same formula that we derived from the previous problem. And what the question says, there's a moment when the x is 6 meters, the y is 8 meters, the z is 10 meters. We know that the x is increasing at the rate of 2 meters per second, and we know that y is increasing at the rate of 3 meters per second. And we're looking for dz dt, but not in general. We're supposed to find it using the information that's given here. So we want to find dz dt at all of this info. So that's what our question is. So what is the info? Well, the info definitely has these x values, or these side values, x, y, and z. It also tells us that x is increasing at the rate of 2 meters per second. So I'll circle that here. So again, we need to write this using mathematical terminology. We need to be able to put it into our formulas. So x is changing, x is increasing, says a derivative. So x is changing is the change in x with respect to what? Well, it's respect to time, because the rate is given as meters per second. So we know that's the change in x over the change in time. That's going to be our meters per second, and that's equal to 2. Similarly, we know that y is increasing or changing at the rate of 3 meters per second. So this is our info that we're going to use into the equation. At this point, since we've already derived the formula for dz dt, we can just use that to plug in all our information. Move me over here and go there. So using this information here, we have dz dt is equal to 2 times the x value times dx dt. Dx dt is 2, remember? And we're just going to plug in all the numbers, just like we, this is supposed to say dy dt. Doesn't look like that, so let me try. Dy dt was 3. And then all this is divided by 2 times z, which is 2 times 10. So that's how we're going to find sort of the answer to these word problems. We're going to find the derivative, then we're going to plug in all the relevant information, and we'll just do a computation here. I think I can do these without too much calculation. 2 times 12 is 12, or 2 times 6 is 12, times 2 is 24. Here we have 2 times 8 is 16, times 3 is 48, and divided by 20. Which is equal to 72 divided by 20. So 72 divided by 2 is 36, and then I'll take a tenth of that, so that's 3.6. Assuming my calculation is correct, this is the change in z over the change in t. What is z? Z is the longest side, the diagonal side length, that's the z, and it's measured in meters. So this is going to be the change in z. I'll just say dz dt at this info is equal to 3.6. The top thing, dz, is going to be in meters. And the bottom thing, t, that's for time. Time is measured in seconds. So this is 3.6 meters per second. So it's important to know what these things mean, especially if we're asked another question, like we are in this problem. Interpret the meaning of the value dz dt in the context of this problem situation. So we're supposed to write a sentence explaining what the 3.6 means. Knowing that it's 3.6 meters per second is going to be really helpful. So we're talking about a derivative. We're talking about the derivative at a particular moment in time. This is the instantaneous rate of change. So at this instant, something is changing. What's changing? Well, z is changing, right? Z is changing at this rate of 3.6 meters per second. It's getting bigger or smaller. It's actually getting bigger because it's a positive rate. Positive rates means that the output value, the z value in this case, is getting bigger. A negative rate means that the output value, the z value, would be getting smaller. So this is z is increasing at this particular rate at a particular moment in time. So that's the key thing to describing or interpreting correctly what a derivative is. Something is changing by some amount at some particular moment. So here, I'll give it an attempt. At the moment when x is 6, y is 8, and z is 10. I guess I should say when the side length, one side length is 6, the other side length is 8, and the other side length is 10. I think you know what I mean when I say x, y, z. I guess it's not as much words as a professional would appear to prefer, but whatever, it's good enough. So at that moment in time, right, when x is 6, y is 8, and z is 10, the diagonal, the longest side, which is our z, is increasing by 3.6 meters for each second. And some people will write in like for each 1 second, and that's fine too. So you can say for each 1 second, or you could say for each second, because it's sort of implied it's 1 second if you just say second. So that would be an interpretation of this derivative value at that moment in time. All right, let's start off with a different word problem and build up from the very beginning so you can see all the steps. Okay, that is very small. Okay, so we'll be doing example B here. It talks about a schematic, which is like a plan for a cubical box, indicates a desired side length of 3 feet. The side lengths are all increasing at the rate of 2 feet per second. How fast is the volume changing in time as the side length increases beyond 3 feet? All right, so that's a simple word problem here. Let's do it step by step, and we can get the solution. So there's a lot of information there. It talks about this box, has a side length of 3, lengths are increasing. We're looking for the volume and how it changes in time. We need to organize that information. Oftentimes, a picture is going to help. Sometimes a table, sometimes equations. Depending on the word problem, you're going to have to choose an appropriate way of organizing the information. And that could be personally. The way you organize the information could be different than the way I organize information, and that's fine. All right, so we're going to have to read carefully. This is a cubical box. So it's not any box, it's a cubical box. That adjective, cubical, means that it's a cube, which means all the sides are the same length. So I'm not great at drawing cubes, but I think it's like a square and another square, and then I connect the sides here. That's close enough. So there's my cube type thing. We know that it has a desired side length of 3. The side lengths are increasing. So one mistake might be to write 3 here because it says the desired length is 3. But remember that the side lengths are increasing, right? These lengths are getting larger, and 3 is a constant, it's a fixed number. 3 does not get larger, it is always 3. So we cannot write 3 there. We need a variable for the side length. I'll be boring and I'll just call this x. So x is a side length. It's going to be 3 at some point. We would like that, but it's going to be changing. It's going to be increasing. I usually denote that to myself just by writing some arrows just to help me remember what's going on there. And because it's a cube, we know that the length, the width, and the depth are all going to be the same variable x. 3 by 3 by 3 or 2 by 2 by 2 or whatever, it's going to be the same. All right, so x is equal to side length. And it's measured in feet. All right. We're told also that the side length is increasing at the rate of 2 feet per second. So the side length, x, is increasing, which means its rate is 2 feet per second. So we know that the rate of change of x in time, we'll denote t as our variable for time. And we'll do that in seconds to match the units in the problem. We know that x is changing in time. It's increasing by 2. So I write that as dx dt is equal to 2. Make sure I'm using the correct mathematical notation and not just writing out the words. That seems to be most of the information. I'll double check it in a moment. It does start with a question. How fast is the volume changing? So we need a variable for volume. We'll just be boring and call that V. Volume is measured in cubic units, so we'll measure this in cubic feet. And we're looking for how fast the volume changes, which is the rate of change in volume in time. But we're not looking for dv dt in general. We're looking for dv dt as the length increases beyond 3 feet. So we're going to find dv dt when something is 3 feet. What's 3? The length is 3 feet or beyond 3 feet. We're going beyond 3 feet. So the length is represented by x. So we're going to say when x is equal to 3. Writing out very carefully what the letters represent helps us quite a bit get this definitively without having to guess at it. Right? Length has got to go beyond 3 feet. X is length, so it's got to be x is 3. All right. So we're looking for dv dt at the moment when x equals 3. We're given some information. In order to find dv dt, we have to find some equation with v in it and differentiate it with respect to t. And you can be flexible a little bit in terms of what equation you want, but sometimes it's much easier to find some equations than other equations. In this equation, the volume of a cube is pretty easy to look up or even remember. The volume of a cube, since any kind of rectangular solid is just length times width times height, the volume formula for a cube, since all of the sides are the same, is x times x times x, or x cubed. So this is a very simple 2-variable equation. Started off kind of easy here. We'll work our way up to multiple variables in a moment, but I want to emphasize a little bit about the process, and we're just going to repeat this for every word problem that we do. So step 1, find an equation that has v in it. Step 2, differentiate it, but we're not going to differentiate it with respect to whatever variable we feel like. We have to differentiate it with respect to the variable that we need. In this case, we need dt in the bottom. So I need to differentiate both sides with respect to t. That will give me a dv dt. Right? Notice that we're not differentiating with respect to x, which might be a guess for some folks if they haven't done a lot of these problems before. So differentiate both sides with respect to t. We do our chain rule. The derivative of v is just 1 times dv dt. The derivative of x cubed is 3x squared times the derivative of x. And the derivative of x is dx dt because we're differentiating with respect to dt. So that's what dv dt is. We are looking for dv dt when x equals 3. So I can finish up this problem. dv dt when x equals 3 would just be plugging in 3. So that'd be 3 times x is 3 squared times dx dt. What do I put in for dx dt, or just do I leave that? Well, it depends if they give you information about what dx dt is, right? Do they tell us what dx dt is in this problem? I'm trying to clear this up and I'm just making a mess of it. Okay. Well, if you remember the information we wrote down, we wrote down that dx dt was 2. So writing down the information, once again, being organized is really going to help you solve these problems. So dv/dt at that moment when x equals 3 is equal to 3 times 3 squared times 2. That's 27 times 2, which is 54. The units of v are cubic feet, and the units of t are seconds. So that's 54 cubic feet per second. And that's the answer to example B. All right. Well, if you feel like you get the idea of it, it's always a great idea to pause the video and see if you can try one. You can try example C. It does have a few more variables in it, but it is a little bit similar to the one before. So it might be a good one to give a go. Maybe I'll leave this visible a little bit for people to reference it if you do want to give it a try. All right, so if you give it a try, great. And I'm going to go through this step by step so you can see the solution as I suggest going along. All right, so read out this problem first of all. It says that there are two children. They're fighting over a rectangular piece of taffy. As they pull from opposite ends of the candy, the length of the rectangle increases at the rate of 7 centimeters per minute, and the width decreases by 3 centimeters a minute. How fast is the area of the taffy changing at the moment when the taffy is 12 centimeters long and 5 centimeters wide? All right, so key thing is there's a rectangular piece of thing, taffy. Doesn't matter if you even know what taffy is. It's a rectangular piece of something, and it's being stretched. They pull from opposite ends where the length is increasing and the width is decreasing. So I'm going to try to give a visual and write down the information. Here's my rectangle in blue. I have a blueberry piece of taffy or something. So there's my thing. It has a length. It has a width. The length is increasing. The width is decreasing. Those arrows are not important. That's just the way I do it to help remind myself of what's going on. This says that I'm going to write down those letters. So L is equal to the length. And we'll see in the problem, it says it's measured in centimeters. So it's in centimeters. W is equal to the width in centimeters. We are told that the length of the rectangle increases at the rate of 7 centimeters per minute. So I need to write that out using some math. That's the change in the length over time is equal to 7. It also says the width is decreasing at the rate of 3 centimeters a minute. So this is getting a little messy. So let me just erase all that. The width decreases by 3 centimeters a minute. So that's dw dt. And notice that it says it's decreasing. So this should be a negative rate, right? A negative slope means that it's going down, which means that the output variable is getting smaller. W is getting smaller, so it has a negative slope, right? Negative rate. Okay, so how fast is the area of the taffy changing is what the question is. So we're looking for how fast area is changing. That's the derivative of area. So we need to have a variable for area. I'll just write that as A. Area is measured in square units or square centimeters. And we're looking for how fast A is changing, which is the derivative of A in time at this moment when the taffy is 12 centimeters long. So the length is 12 and 5 centimeters wide. So the width is 5. So we're looking for the change in A with respect to T at this moment that the L is 12 and the W is 5. Okay, well, I'll put a little equals question mark here just to remind me that's the question. Okay, so that's the setup for the problem. Write down the information in an organized way, using calculus, using math, that kind of thing. In order to find dA/dt, we need a formula for A. We need some sort of equation that includes the letter A, and we differentiate it with respect to T. So what's the formula for A? Well, A is the area, and you may remember the area of a rectangle. So we have a rectangle here. Area of rectangle is length times width. So we'll write area is equal to length times width. And we're looking for the derivative with respect to t. So I'm going to take this equation and I'm going to differentiate it so I can find dA dt. But because it's dA dt, I need to differentiate with respect to t. If you write down carefully what you're looking for, it kind of guides itself. Since we're looking for dA dt, it's got to be dt down there. So there's no doubt in my mind we need to differentiate with respect to t. Now we're going to do some mechanical. We're just going to do some actual calculus. Derivative A is 1 times dA dt, or just dA dt. Derivative of L times W. This is L times W. That is a multiplication of two variables. Remember, L and W are both variables. So when you're multiplying two things together, two functions together, two variables together, and you're looking for the derivative, that's the product rule. So we're going to use the product rule here to find the derivative of L times W. So it's the derivative of the first times the second plus the derivative of the second times the first, whatever symmetrical version of that you use. You'll get the exact same result, even if you do it in a slightly different order. All right, so that's what dA dt is. We are looking for dA dt at a particular moment when L is equal to 12 and W is equal to 5. So I will now plug in some information. So it starts off with dL dt, but fortunately, remember, we already wrote down what dL dt, it's 7. The width is 5. dW dt is -3. And L is 12. And that's how you do it. You set up the problem by reading the words and writing them down in terms of mathematical information. You find the equation that you are looking for to differentiate. You differentiate with respect to the correct variable, in this case t. Then you plug in all the numbers and you're done. Let's get some final answer here. 7 times 3 is 35. -3 times 12 is -36. So this is -1. -1 what's? Well, the thing we just found was dA dt. A is area. It's measured in square centimeters. So this is -1 square centimeters. And then the bottom variable is t. Time is measured in, oh, I didn't say what time is measured in. I forgot my time variable, which is why I don't know what to do now. So if I had written time up here, it might have been easier at this point, but I have to kind of backtrack. What is time measured in this problem? Minutes. All right, so if I read the problem here, I can pick out that time is measured in minutes. So if I'd written that ahead of time, maybe it would have saved me a little bit of work instead of going back and rereading the problem. But no worries, I got it now. So this is dA over dt, so it's centimeters squared over minutes. So that's, whoops. That's my answer for the change in L over change in T at this particular moment in time. So when the length is 12 and the width is 5, I actually know my area is decreasing. Remember, a negative rate means that it's decreasing. So my area is decreasing at the rate of 1 square centimeter every minute at that moment. All right, how'd you do? Okay. I actually have a little bonus problem here. All these problems I want you to sort of feel at some point when you start becoming good at these problems are kind of the same. You just write down the formula, you differentiate, plug in the numbers, right? Mechanically, it looks kind of complicated because you have all these derivatives and things going on, but you will get very comfortable with those after a while, and then it'll feel like these problems are not as difficult as they are, or as they usually are, I should say. This section 3.9 oftentimes has labels one of the harder sections in first year calculus. These related rates problems, one of the three things students say are really, really tough in calculus 1. The other two things, if you want to know, are curve sketching, where we do a lot of stuff with first and second derivatives, and then maximum minimum word problem. So another type of word problem, but we are trying to find the largest or the smallest of something. Those are the top three things that usually students indicate are the toughest parts of Calc 1. So I'm hoping that with some practice here, one of those top three tough ones, these related rates problems, won't be so tough after all. All right, so let's just look at the same scenario. I have a little bonus problem right here. So same Taffy problem, but this time we're determining how fast the perimeter is changing at this moment. No problem, no problem at all. All we need is a variable for perimeter. So we'll say P is equal to the perimeter. Perimeter is a type of length, so that would be measured in centimeters. I need a formula. If I'm looking for how fast the perimeter is changing, that means I'm looking for how fast P is changing in time. In order to find how fast P is changing in time, we need a formula for the perimeter, right? We got to find a formula or an equation that involves the letter we're looking for, and then differentiate respect to the letter we need, and that's how we find our answer. So to find dp/dt at this particular information, we need to find some equation with P in it. Since it's a rectangle, you can look up, or perhaps you remember, that the perimeter is 2 times the length plus 2 times the width. That's our formula for the perimeter of a rectangle. And then we just differentiate this. We're going to differentiate respect to t because we need a dp/dt. So it's got to be a t on the bottom. You don't have to wonder why. That's what we're looking for. The derivative of p with respect to t is called dp/dt. The derivative of this stuff, this is no longer a product rule. It's a sum rule, so we can differentiate them separately. The 2 is a number. So again, not a product rule. It's just a constant that stays as part of our derivative. So the 2 hangs out. The derivative L is called dl dt. And then similarly, we get a 2 times the derivative W, which is dw dt. And then just like before, we just plug in all the information and we get our answer for this bonus problem. So dp/dt at this given information is equal to 2 times dl dt. Let me zoom out just a little bit. And dl dt, I think, was a little higher here. dl dt was, let's see, 7. Okay. All right, so let me do this. Okay, there we go. So it's 2 times dl dt, which is 2 times 7, plus 2 times dw dt. dw dt is -3. And just like before, we do some computations. We write down the correct units. P perimeter is measured in centimeters. T time measured in minutes. So at this moment, when the area is getting smaller, it's decreasing at the rate of 1 square centimeter per minute. The perimeter is actually increasing at the rate of 8 centimeters per minute. All right, there's a little bonus problem. All right, I'm just going to do some more examples. That'll be today's video. It's just doing some more of these examples, just so you can see more and more sort of setups and conclusions for these word problems. From my perspective, I'm really not going to do much different for the rest of the video. The only thing different is going to be we're going to be doing different problems, different word problems, but the strategy is going to be the same each time. Okay, I do have an extra bonus problem over here. We'll get to that in a minute. I'm supposed to be able to move it, but oh, there we go. Move it over here for the moment. Okay, let's focus on these problems here. Okay. So we're going to do example D together here. There's a girl, she's 1 meter tall, and she's walking away from a 5-meter high light pole at a constant rate of 2 meters per second. At what rate is her shadow length on the ground from where her body blocks the light from the pole changing at the moment when she is 3 meters from the light pole? These kinds of word problems, I remember when I first did them, they were very kind of challenging to make a picture out of because you got lots of things. You got the girl, you got the light, you got the pole, lots of things going on. It might be really good just to give it a try. You may not actually get a picture which you can clearly capture all the information, but I think going through the process of seeing what you need to put down and where it might go can help you remember when you do get the answer or when you see my answer where things are, because there are a lot of these problems where you have things relative to other things that are moving, and it can be difficult if you haven't practiced a few of these to be able to draw an effective picture or at least organize the information in an effective way. So give it a go if you want. I'm going to, in a moment, do my version of the picture. Okay, here we go. So there's a girl. So I'm just going to do my picture of a girl. I'm not a good artist here. There's my girl. She is 1 meter tall. So this right here is 1 meter. Well, I'm going to make her have longer legs. So she's, on the ground. You can't draw very well, as you know. So there's my taller girl. She is walking away from a 5-meter high light pole. So it doesn't matter whether you draw the light pole over here to the left or to the right. I'm going to draw it to the right just because I have space on my screen. So here's my pole and some sort of light here. And to remind myself, I'll call this light pole. I guess this is the light and this is the pole over here. So the light pole is over there. A girl 1 meter tall is walking away from a 5-meter high light pole. Okay, so this guy is 5 meters tall. Okay, so we got a 5-meter tall light pole. We got a 1 meter tall girl. She is walking away. So she is going this way. The girl is walking away from the pole. At what rate is her shadow length? Her shadow length on the ground. So I need a ground. So my ground will be green. There's my ground. She's walking along the ground away from the light pole. At what rate is her shadow length? The shadow length is on the ground from where her body blocks the light from the pole. Okay, so there's light from the pole, I guess in all directions. So the light in the pole shines down here and hits the ground. It also shines on our friend, but it cannot shine through our friend. She is not an invisible person. So the best the light can do is shine right above her head. So right over here, this stuff is where the light gets blocked. So light also goes here, light goes here, light goes everywhere. But she blocks part of the light, meaning that the part after her body, where her body blocks the light, is where the shadow is. So this right here, let me put that in black. This right here is my shadow. Okay, at what rate is her shadow length on the ground from where her body blocks the light changing? So it's also getting into a question. It's saying, at what rate is her shadow length changing? So I need some letters. Now, the shadow length is changing, so that's got to be a letter. I'll call that L. It looks like we're doing things in meters, so I'll do in meters. I'll change it if I need to, but so far it looks like we're doing things in meters. We need time, so we'll do T is equal to time. Do we have any measurement of time in here? We have seconds, so I'll do time in seconds. All right, let's go back to the problem. A girl, 1 meter tall, walks away from a 5-meter high light pole at a constant rate of 2 meters per second. So she is walking away from the light pole. So again, I kind of wrote it down here, but she's walking away from the light pole. As she walks away from the light pole, then it looks like this shadow length is changing. When she ends up over here, then the shadow length is going to be different, right? Okay. At what rate? Okay, she walks away at a constant rate of 2 meters per second. Well, it doesn't say the shadow length is changing at 2 meters per second. It says she's walking away from the pole. So we need a way of writing down her speed, right? Speed is distance over time. So her distance over time, we need to figure out how fast we're told how fast her distance over time is changing. It's 2 meters per second. So we need a variable for distance. Since things are being measured relative to the pole, then we will call sort of a distance, do it in, I'll do it in black as well, from her to the pole, that distance right there. I don't want to call it D, I'll just call it X. X is equal to distance of girl to the pole. And that's again measured in meters. We need that because we're told that she's walking away from this light pole at a rate. So we're told that the distance she has from the light pole is changing. So that is telling us something about her distance, and we need a variable to represent the distance. So what are we told about that x, that distance? We said that she's walking away at the rate of 2 meters per second. So that's the change in x over the change in time is equal to 2. You should pause your thinking and say, is that a positive 2 or a negative 2? It's not clear from the English wording whether it's a positive or a negative. It's a positive if x is getting bigger, and it's a negative if x is getting smaller. Remember, this rate, the slope is just measuring how the output variable is changing. In this case, how x is changing. If it's getting bigger, that means we're adding to x, so it's a positive rate. If x is getting smaller, it's a negative, so it is being smaller. Okay. So in this problem, x is the distance along the ground from our friend to the pole, and she's walking this way. Remember, she's walking this way. As she walks, does the x get bigger or smaller? It gets bigger, right? When she walks over here, she is now further away from the pole, and x has increased. So we know that x is positive 2. It could have been negative 2, and we might have gotten the wrong answer. In this case, it is a positive 2. I'm just going to emphasize plus 2 here, just to remind myself I already checked it. But that is something that you may be tricked by in terms of the homework. Double check to see if you know whether the rate is positive or negative. Okay, we have a girl 1 meter tall walking away from a 5 meter light pole at a rate of 2 meters per second. At what rate is her shadow length changing? So this is the question. At what rate is her shadow length changing? Well, we know our shadow length is L, so we're looking for DL over D what? Shadow length is changing at this moment, so that's in time. So how fast is the change in L over the change in time? At the moment when she is 3 meters, so at the moment when she is 3 meters from the pole. So the distance to the pole is X. So we're looking for DL. That's supposed to say T, but it looks a little bit more like a Z. Let me just clarify that. We're looking for DL dt at the moment when X is equal to 3. Question mark. All right, so that was the setup. So again, it's a word problem, and this is oftentimes one of the harder parts of a word problem. It's just organizing the information. I organized the information in terms of a picture. The picture helped me decide what letters I needed. I wrote down what each letter measured. I wrote down some information in terms of a derivative, dx dt, and I wrote down my question in terms of derivative, dl dt. So all that is what you're going to need to do in solving these word problems. That's usually what you need to practice the most once you get the idea of how derivatives work. All right, to find dl dt, we need a formula for L, and we need to differentiate it with respect to t. Now, the formula for L can be any equation as long as there's an L in it. So we need to find an equation that has an L in it. So this is a triangle type problem. I'm going to make it look more like a triangle because right now I have all these like light rays and stuff. So I'm just going to simplify this. Here's the pole. It's supposed to be straight up and down. Here's the pole. Here's the ground. This is the girl right there. This distance is X. We have a shadow. So this is the shadow length right here. Do we have, oh yeah, we have L for shadow. So L right here. So from here to here is L. This is where the shadow is. I'll make another little ray up here going to the top of the pole. Oh, the girl is 5 meters tall, so this has got to be 5. Girl 5 meter tall. I guess the shadow goes here then to where the end of that little triangle is. So yes, there we go. So we have a right triangle right here. We have a pole. Oh, it's 5 meters. There we go. 5 meters there. Oh, the girl is not 5. The girl is 1. It's not super tall girl, just a regular height girl. Okay, so let me change this to a 1. And let's see if I've redrawn my figure without all the fancy artwork in there. 5 meter tall pole, 1 meter tall girl, X distance from the ground to the girl, L distance from the girl to the end of the shadow. I think I got it all in there. So that is my situation. I have actually 2 triangles. I have this sort of inner triangle here, and then I have a bigger triangle, a right triangle, a bigger right triangle. There's 2 right triangles here. I guess there's lots of triangles, but I'm talking about right triangles. There's 2 triangles there. All right, so now we need some formula involving L. All right, I'm going to pause the video just for 1 second. Okay, I'm back. Okay, so we left off with saying that we need some equation that has L in it in order to differentiate it and find what we're looking for, which I believe I wrote here on the side as dLdt. Yeah, dLdt when x equals 3. All right, so right triangle makes us think about the Pythagorean theorem, which is quite natural for right triangle problems. The Pythagorean theorem involves 3 side lengths, right? A and B and C, right? Or in this case, something along the ground, something along the height, and the diagonal. We do not have any information about the diagonals. We don't know this diagonal. We don't know this diagonal. There's nothing in the problem which tells us about the diagonal. So if you're thinking Pythagorean theorem, that's a great idea. It turns out it does not work in this problem. It won't give us an equation in any easy way. You can try to writing a couple of Pythagorean theorems and then trying to eliminate the variable, and that actually could work, but it's a lot more work than perhaps another approach, which is similar triangles. So we do have a couple of triangles here. We actually have 3 triangles. We have the red triangle, the green triangle, and the blue triangle, the smaller triangle right here. And we can use these triangles and similar triangles from our geometry to write down an equation. So we have this little blue triangle. I'm going to write it down here below so it's easier for you guys to see. This blue triangle has a right angle here, and it has an angle that I'll just put here in red, that angle right there. Right? The green triangle has a right angle, but this angle is not the same as the red angle. It's a different angle, right? Different spread because it's goes higher than the other one. So it's not the same angle. And then we have this red triangle, which is the big one. And the red triangle goes from here to here to here, has a right angle, and the angle here is shared. So it's the same angle as here. So the similar triangles that are similar are triangles that have the same angles. So this guy right here and this guy right here are similar triangles. Once they have 2 equal angles, the third angle also has to be equal because all the angles add up to 180. So we know that all 3 angles are the same, just that one's a bigger version of the other one. That's called similar triangles. Similar triangles. Okay, so we can use the similar triangles to write down our equation. Let's put down some letters here. So in our blue triangle, this here is L. This is 1. We don't know the diagonal. And in the red triangle, the big triangle, along the ground, X goes from here to here, and L goes from here to here. So the total length along the bottom, along the ground, is L plus X, right? L plus X gives that whole bottom part. And the height here is 5. And the way similar triangles work is it's just a scale model. Like if one side is twice as big as the other side, then everything is twice as big, right? It's just everything is multiplied by the constant proportion, right? So since we know that this is 5 times bigger, right? Instead of a height of 1, you have a height of 5. We know that the lengths have to be 5 times bigger. So we know that L plus X is just 5 times bigger than L. Now, the way the math people write this is a little bit different. So I'm going to write the math way. The way they write it is the ratio of 5 to 1. That's the ratio of the big triangle to the small triangle, like vertical sides, is got to be the same as the ratio of the other side. So in this case, L plus X for the big triangle and L for the small triangle. So this is the statement of proportionality that you would see if you look at a math book or equation. But it basically says everything's got to be 5 times bigger. If one side is 5 times bigger, everything's 5 times bigger. Okay, so that's our equation. Notice that's an equation with L in it. Hey, that's what we're looking for. We're looking for an equation for L, so we could differentiate it. If I simplify this by multiplying both sides by L, I end up with the equation 5L is equal to L plus X. And I'm going to write that over here on the left-hand side. Now, since we're looking for dl dt, we have an equation involving L in it. We can now just differentiate respect to t, and we will, voila, find dl dt. Now, if you want, you could actually simplify this. It's really not necessary, but I could subtract L on both sides because, it might be nicer to simplify before you do the derivative step. So if you see that, great. If you don't, it still works fine. You can just differentiate it without simplifying ahead of time. It's just a little bit more work if you don't do that. So I do want to differentiate this respect to t. So I'll do d dt on both sides. The derivative of 4L with respect to t. 4 comes along for the ride. The derivative of L is called dl dt. And the derivative of x is not 1 because we're differentiating with respect to t. So the derivative of x with respect to t is called dx dt. And if you write down the correct letters, you just follow the instructions, and you know it's not dx dx, you know it's dx dt. And so 4 dl dt is equal to dx dt, which means if I divide by 4, I get dl dt is equal to 1/4 of dx dt. Now, our problem asks for dl dt when x equals 3. So dl dt at the moment that x equals 3, this looks kind of messy. So at the moment, dl dt when x equals 3, well, there's no x to plug into this formula. So I don't have to plug in 3 anywhere because it just says 1/4 dx dt. Do I know dx dt? Yes, I know it's positive 2. So I plug in all the information I have, and that tells me that dl dt at this moment when x equals 3, and other moments, by the way, is equal to 1/2. What are the units? Well, L is the top variable, and that's measured in meters. And T is the bottom variable, that's measured in seconds. So at this moment, the length of the shadow is increasing at the rate of 1/2 of a meter per second, or 1 meter every 2 seconds. All right, so there's the girl walking problem. There's a bunch of things where something relative, one plane relative to a radio station. There's lots of things that have the same kind of feel. So once you do a few of those, you might be able to see the pattern of how to write down. And Pythagorean theorem is great, but doesn't always work. I wanted to show you a problem where similar triangles works really well in terms of developing an equation involving the letter that we need, an L in this case. All right, let's charge ahead and look at another example, another word problem. And this, I think, will be the last one for this video. So example E, we have a cylindrical tank with its circular base facing down, is 8 feet high and 2 feet in radius. It starts off full of water, but the water is leaking out through a hole in the bottom at the rate of 0.5 cubic feet per minute, or half a cubic foot per minute. Find the rate at which the water level is changing after 2 minutes. Oh dear. So once again, we need to figure out how to encapsulate all of this information in a usable way. Well, let's just start drawing a picture of a cylindrical tank. Its circular base is facing down. So I'll draw something like a circle here and a circle here and connect them. That's the best kind of cylinder I can draw. The circular base is facing down. It is 8 feet high. So this is 8. And 2 feet in radius. So 2 feet in radius. Okay. Cylindrical tank with its circular base facing down is 8 feet high and 2 feet in radius. It starts off full of water. All right, so you're full of water. Here's the water, all full of water. But the water is leaking out through a hole in the bottom at the rate of 0.5 cubic foot per minute. All right, so there's some little hole in the bottom here. Maybe I'll make that this. And water is leaking out. How do I draw water droplets? Maybe like this. Okay, don't make fun of my drawing. So there's a water droplets and it's kind of spilling and to make a little puddle here. So water is dripping out. And so the water is dripping out at the rate of 0.5 cubic feet per minute. Okay, we're going to have to use some variables in a moment. Find the rate at which the water level is changing. So we need to know where the water level is. Well, the water level starts off at the top because it's full, but we know that it goes down. So we know at some point the water level is lower. So I'm going to get rid of this blue water stuff so I can more easily see my picture. Okay, so at some point we get a water level which is lower. So we'll call this a water level. And I know that my water level is going down, right? It's decreasing. We're looking at how fast the water level is changing after 2 minutes. So the water level, we can measure the water level from the bottom going up or from the top going down. It doesn't matter. You just have to decide. And so I'll just go from the top going up because, sort of like the y-axis starts 0 at the bottom. So this is my water level right here. From here to here. I need a variable for that. We'll call it L for level. So the water level is from there to there. It is decreasing, so it's getting smaller. And we are looking for the rate at which the water level is changing. So we're looking for dl dt, probably at some moment in time, but I'll just leave it like that for a moment. All right. We have this water leaking out. What the heck is going on there? Water was the stuff inside. How do we measure water inside a cubical tank? Well, one hint may be looking at the units. Notice it says cubic feet per minute. Cubic feet is a measure of volume. And that actually makes sense because the volume of water is leaking out through the bottom, and the volume of water inside our cylinder is getting less. That's why the water level is going down, because the volume is going down. So we need a letter for V. I forgot to write down my letter for L. So L is equal to the water level. And that's from the bottom. And we're measuring from the bottom. And V is equal to the volume. And we're going to say volume in the tank. So I know the volume of the puddle is getting bigger, but the volume of the tank is getting smaller. So we know that the the volume level is changing. And it says it's leaking out at the rate of 0.5 cubic feet per minute. So that's 0.5, right? And that's cubic feet per minute. Notice that the volume of water in the tank is decreasing. So once again, make sure to double check. This is a negative rate because the amount of volume is getting smaller. So it's negative 0.5. A cylindrical tank with its circular base facing down is 8 feet high. Got the 8. 2 feet in radius. Got the 2. Starts off full of water. So we know at time 0, the volume is all the way. It starts leaking out through a hole in the bottom at the rate of 0.5 cubic feet per minute. We got that. Find the rate at which the water level is changing after 2 minutes. Okay, that's what I forgot. So we're looking for DLDT at the moment that T is equal to 2. All right. So if we're looking for DLDT, then we need to find some equation involving L, and then we need to differentiate it with respect to T, in this case, to find DLDT. All right, so I'm going to pause the video to encourage you to see if you can come up with some equation involving L. You don't have to finish the problem if you don't want to, but see if you could come up with some equation that involves the letter L so we can differentiate it. Now, there's a hint. Because we were given information about the change in volume, about volume dV/dt, your formula might also involve the letter V. Since there's dV/dt, it might be, it might be sort of a hint that since we know information about V, V may be part of our equation. All right, so see if you can give it a go. See if you can write down some equation. It's okay if you can't come up with it, but give it a think. See if you can come up with an equation that involves the letter L. Okay, so there are many different ways you can get an equation for L. Some of you may have done some similar figures, which works well. Here's an approach that I'll suggest. Again, not trying to say this is the way to do it. It's just one way of thinking about it. The water level right here is kind of a circle right here. The water level is a circle there. And so we can find out the volume of this sort of water that's still left in the tank. So this figure is a cylinder. So the volume of a cylinder is pi r squared times the height. In our particular problem, the r is fixed at 2. It's always 2. And the height of our cylinder we've written as L. So using those values, we get pi times 2 squared times L. So that's the volume that involves the letter L. So I'll just clean this up a little bit. 4 pi L. And if you did it a different way, what you found would be equivalent to 4 pi L. Okay, so this is an equation that involves the letter we want, L. So now we're going to differentiate it. If you want, you can divide by 4 pi. I will choose not to do that on this particular problem. I'll just go ahead and differentiate it. What letter do I differentiate with respect to? Well, let's go look to see what we're looking for. We're looking for DLDT, so I need to differentiate with respect to T. The derivative V with respect to T is called dV/dt. The 4 pi does not change anything. And the derivative of L is dLdt. And now I know what dLdt is. dLdt is equal to all that stuff there. I'll just kind of write it like this, divided by 4 pi. And now if I'm looking for dLdt at a particular moment, specifically when time is 2 seconds, or 2, whatever it is. What am I looking for? dLdt at t equals 2, yes. Then I just plug in a 2. Oh, I know what dV/dt is. dV/dt was given as negative 0.5. And 4 pi is 4 pi. And so whatever negative 0.5 divided by 4 pi is, that's the change in the length. The length is measured in, where's length? Water level from the bottom. It didn't say the units here. What is water level measured in? Feet. And t is time. What is time measured in? Minutes. So this would be feet per minute. All right, so there's how fast the length is changing in time. All right, I do have a bonus problem if you want to try a bonus problem. Just over here. Oops. Let's try grabbing this way. Nope. There we go. So I did come up with a bonus problem, which is talking about a spherical balloon. So if you want to give that a go, I will just post my answer down below here. I'm not going to go through it step by step, but it might be a good one if you want to do some extra practice. Let me zoom out. So the last problem a little bit. And then, yeah, if you want to give this a go, in a moment, I will just show you the solution, and then we will be done with today's video. I hope you enjoyed. Hope you have an enjoyable day, and I hope you found this useful. Please let me know if you have any questions. All right, so there's my solution with the various steps. Please reach out to you for any questions, and I hope you have a wonderful day. Thanks.